Hello and welcome to lesson 36, Radioactivity. All right, so this is definitely going to be more of a reading one. It's actually a really good read. It's a story again, right? So what I'm going to do in this one, going to kind of give you the quick notes on all of this stuff, give you just a bit of context on the story. I still would like you guys to make sure you read through this because there is bits of information that I'm probably not going to cover here that you still will need to know. But I'll just kind of go over the story and make sure you understand what happened. All right, so what we start with is this guy named Henry Becquerel in 1896 was doing experiments to find like X-rays. Right, they knew about the electromagnetic spectrum, right, and they were trying to find, okay, can we find even shorter and higher energy waves, right, down at the one end. Um, so what he was doing is they had these things called phosphorescent crystals, and put them on photographic plates. And what that did was, if you shone light on these plates at really high energies, these plates, these phosphorescent screens, would emit light at a lower frequency. So actually, so you could see them. It would turn things that were, like, let's say, in the X-ray range, and they would absorb those, but then only emit things. Not only emit, but it would emit things in our visible spectrum, right? So that was a way of detecting, hopefully, X-rays, right? Because they didn't have the technology we have today, right? They couldn't see these X-rays. So that was what he did. But then he ended up putting a piece of material, which was a uranium compound, in a drawer with the photographic plate, and then noticed that it actually was like the phosphorescent screen was glowing just because of the uranium compound that was in there. So it wasn't exposed to the sun or any kind of like cosmic rays or anything like that. It was all coming from this uranium compound, which was kind of an accident, but turned out to be kind of cool. So he accidentally discovered radioactivity. All right, so what is this radioactivity? So next two famous people, we've got Marie and Perry Curie. You, she, Marie Curie is really the famous one that you'll hear about as being like one of the people who discovered radioactive or X-rays. Um, so she discovered that this decay is happening from inside. So this is like a nucleus, right? Whatever it is happening just spontaneously. So this atom, those are protons and neutrons in this nucleus, will just spontaneously emit radiation out of it, just randomly. It didn't seem like it mattered whether you heat it up or anything like that. It happens because of something happening internally inside the atom. For her work with X-rays and radioactivity, she received a Nobel Prize in chemistry. All right, then along comes Ernest Rutherford. He comes up a lot, right? Studied it more and discovered and named two particles emitted in radioactive emission. So this thing that I'm saying, like it's emitting spontaneously out of the nucleus, there's only certain things that it'll be. The first ones that they discovered were, well, alpha decay. We're going to talk about this, beta decay, and gamma rays. Those are like the three things that they discovered first. So a little bit about both, or about all three. You guys will need to know kind of in detail about these different forms of radiation and the effects that they have. So these are important. All right, so alpha particles. So alpha particles, we've talked about this before. Alpha particle is really a helium nucleus, right? It's been stripped of all its electrons, so it's just two protons, two neutrons, and it will just spontaneously emit from that nucleus, right? Leaving behind a different atom, right? Because if it lost two protons, it's now something different, right? It's lost two protons, so it would be some different atom on the periodic table. But yeah, that will just happen randomly. And they're ejected at high speeds, but have a range only a few centimeters in air, and they're stopped by an ordinary sheet of aluminum foil. Really, you can imagine that this is happening because it's a pretty big thing in comparison to the other ones we're going to talk about, right? An alpha particle has two protons and two neutrons. That's going to be a lot bigger than, let's say, in the next one where we're talking about it just being an electron being emitted, right? This is like a big thing. It's going to bump into your air molecules and into your sheet of aluminum foil, so it just won't go very far. Even though they can have high speeds to begin with, it's going to bump around into all the air molecules and slow down pretty quickly. All right, beta particles. Beta particles really are electrons, so it'll eject a high energy, so high speed electron, and we've seen this a little bit so far, but this is the symbol for an electron, which, you know, it has a 0 for its atomic mass, right? Because it's essentially 0, and really these numbers, this number up top, is really talking about the nucleons, right? So protons or neutrons, so that makes sense that that'd be 0. And then an electron has a charge of -1. Okay, they are ejected at varying speeds, so sometimes it's like almost the speed of light in certain cases, but it's kind of random. And then high energy beta particles are able to penetrate several centimeters of aluminum. Well, it just makes sense because it's smaller, right? It's going to go farther into that aluminum plate or air or whatever you're comparing it to. Okay, and then lastly, we got gamma rays. So gamma rays are electromagnetic radiation, right? So this symbol is the gamma symbol. And we've got 0, 0. Well, that makes sense. You've got no nucleons and you've got no charge because it's a photon. And they're very short wavelengths, right? So they can vary. Wavelengths and energies can vary, which makes sense, right? If you change the energy, you would also change the wavelength. And they can penetrate 30 centimeters of lead and 2 kilometers of air, which really makes sense again because they're just a tiny little wavelength, right? That can penetrate pretty far. It can go right through you, really. All right. So how can we figure out what's being emitted? Well, we've done this in the past in other units, right? In our magnetism unit, where if you shoot a charged particle, so we're back to hand rules, right? So imagine you've got some particle and you don't know what it is, and it's traveling this way. If you're using your hand rule, so your fingers would be pointed into the board or into the paper, right? Because the X is there. So let's say I'm using my left hand over here. My thumb would be in the direction of the arrow, right? My fingers are into the board. Well, that's going to cause a deflecting force down, right? And would cause this thing to go into a circle. So that makes sense. If I'm using my left hand, that's because it's a negatively charged particle. That's the beta particle, right? And then the other side of that, if I look at, if I use my right hand, let's call that's the blue one, well, that's going to be the other way, right? That's going to be a deflecting force upward, causing this thing to go into a circle. Now, just while we're on the difference between so that should have been alpha particle, yeah, up there. The difference between an alpha particle and the beta particle or an electron. Notice too that this one, right? This one went farther than this one did. Think about for a second why that might be. There, I'll give you a second. The alpha particle, it has more mass, right? So it has more momentum. It's going to travel farther. It's going to keep its speed longer, right? So it'll make more of a drawn out arc. And then the beta particle or the electron, well, that's really light, right? So it's going to be able to change its direction really easily. It has less momentum, right? Momentum is mass times velocity. So really, really small momentum mass is going to make it have a small momentum, yada yada, right? So it won't go as far. Okay, and then lastly, if we see one going straight through, well, that makes sense for a gamma ray, for a wave, right? Because waves aren't affected by magnetic fields, so they would just travel straight on through like nothing happened. It doesn't care about magnetic fields, so that's how we know the differences between them. We're gonna get into how could you possibly see this, right? We're gonna get into this in another lesson here, where we'll talk about things like bubble chambers and cloud chambers, and they're actually able to see these things happening. All right. Okay, and then we've actually kind of talked about this in the last lesson, how sometimes when things undergo decay, they can actually go through a few steps, right? So this one will go down to that, and then emit a particle, and then that'll happen all the way down, you know, just emit like new particles all the way down these series of steps. It can be kind of complicated. We don't need to know exactly what would happen all the way down. That's actually, well, it's kind of random for one thing, and it's kind of above what we're doing in Physics 30. But you do just need to know that this is kind of the path that it would take, right? Things can decay into other things, and then they're still unstable, so then they'll decay down once again. All right, so we've done this before too, kind of. There's just a little twist on this. It says write complete nuclear equations for the following. So we got beta decay of thorium-234. This is a typical type of question, by the way, right? So diploma and MI tests would look like this. So we've got thorium-234, so you'd write it out like this. You'd find on your periodic table that it's 90 for thorium. And then you know it's beta decay, so beta would look like this, right? Well, what's the missing particle? Well, conservation of nucleons and conservation of charge. So conservation of nucleons, well, there was 234 before. There's got to be 234 after, so this has to be 234, right? You can see a little equation there if you want to look at it algebraically. And then your conservation of charge for the bottom. Well, we haven't really talked much about like there being a negative up until now, but it's gonna, like the negative will play a part here, right? So if I had a charge of positive 90 to begin with, and then I've got negative 1 over here, well, this has to be not 89 but 91, because if this is 91 minus 1, I've got 90 on both sides. So okay, so 91 ends up being Pa, protactinium. All right. So just one last little thing here. We don't talk much about this, but that little star there at the end, that means that this thing is still unstable. They'll make that little symbol there saying it's not it's not a stable isotope, so it will really decay into something else shortly, like really shortly, like fractions of a second. All right, so it turns out though, I'll let you guys look through this one too. It's a similar thing. Beta minus decay though is going to involve more than just emissions of electrons. So this isn't a complete question. There's another part to it. So we'll get into the story of this. So conservation laws applied to alpha decay. So helium nucleus, right? So what happened here? So what happened was that if we look at this from like Einstein's mass energy equivalence, right? Well, we should be able to say that if you've got some particle to begin with, right? Again, like, and then this parent nucleus decays into some daughter nucleus, right? So whatever. This isn't the right number, but just bear with me here. Let's say like an alpha particle was ejected or something like that, right? Then what we should be able to say is, like, looking at the mass difference between the parent, right, that one, and the daughter nuclei, right? We should be able to say, well, the missing energy should be in the form of Ek, right? It should be in the form of the energy that this alpha particle has. So they could test this, and they did. They said, okay, well, if that's true, this missing energy, we can calculate that using E is equal to mc squared to figure out the kinetic energy. And then that kinetic energy should be this, like, wrapped up into the speed of the alpha particle. And that should affect how far, let's say, this alpha particle is embedded into a certain material. So that's exactly what they did. So they had a few different materials. So thorium-232 they did this with. They did it with, what was the other one? Radium. And it turned out that they had different kinetic energies just based on the atom that it was, which really made sense, right? The mass defect was the kinetic energy. So this all added up. So our conservation of mass energy was really conserved at this point, right? Actually, I should say that it was conserved, but not quite. Every once in a while, it was like most, like, I forget what number, how many percent it was, but it was like by far the most of these helium or these alpha particles had the same energy. Some didn't, and it turned out the reason for it we're going to talk about this in a minute. You remember those energy level diagrams that we had for electrons going all the way up, right up until the ionization level? Well, it turns out that nuclei have the same thing. They can exist in different energy states. So they like to be hanging around at ground zero, right, at our lowest energy, but sometimes they can be hanging around up here. And if that's the case, when they eject our helium nucleus, they'll have more energy than they would if they were up in energy level 1. And it would be even faster if it was up in energy level, 1, 2, 3, 4, 1, 2, 3, 4, right? They would have more energy than it would if it was dropping down from 1 down to 0, right? So this just the same as our electron energy levels that we did in the last unit. It turns out that the nucleus of an atom actually follows the same thing. So, but they could figure that out mathematically why that was, and they could do something similar before. So the point is, though, is that this was all making sense. So conservation of alpha decay checked out. It worked, right? So everybody was happy. Physics was making sense. But conservation laws applied to beta decay wasn't so nice. This wasn't working out. So what you guys will read through here is that these beta particles, or these electrons that were being emitted from our nucleus, right? So you've got an electron that will just randomly be emitted from the particle here. You should be able to say that the speed of this electron is related to the missing mass, right? They can figure out the mass that was missing between that and the daughter nuclei that be created, and say, okay, well, that's how fast our electron must be going. But it didn't work out that way. They were usually around like 40%, right, or something like that of the actual speed. It was kind of all over the place. Sometimes it was like the max speed, sometimes it was like hardly anything. So this was confusing. This was pretty much saying that like our conservation of energy, conservation, so E is equal to mc squared, right? That mass and energy are equivalent, so any missing mass should just be in the form of energy, or vice versa. This was kind of breaking down. It was like we were missing mass energy, right? So, okay. Along came a guy named Wolfgang Pauli. He's one of the founders of quantum mechanics. He suggested a explanation. He proposed that if the beta particle did not carry off all the available energy, the remainder must be given to a second particle. So just kind of think about that for a second. That's weird. He's just like, well, I really, really like this whole conservation of energy thing, right? Because we have a lot of reason to believe it's true. Physics is based on that. We've got this situation where it seems like the laws of physics are being violated. So he says, well, I'm going to insert magic particle here, right? So conservation of energy isn't being conserved. So we'll just say, well, there's this invisible particle where it is being conserved. So he called it. Well, I'm getting a little ahead of myself. So he knew that this particle must be neutral, right? Because if I look at this, my charge before and my charge after, right? If I've got I never really talked about this either. This will happen, and we'll talk a lot about it, where you get a neutron will spontaneously decay into a proton, which is weird, right? Just one turns into the other, plus an electron. And the reason why this works out is because before I've got a charge of 0. After 1 plus -1, I've still got a charge of 0. And then my conservation of nucleons, I've got 1 and 1 and 0, right? So it all adds up. So I get the right, like it should be an electron coming out of this thing. But it should be plus something else. And this is what Pauli was saying. This plus something else has to exist. He knew this plus something else must have no charge because we're good. It already adds up to 0. And it must have no mass too, or it must be like, on the order of magnitude of like an electron or a photon, just having no mass at all. Okay, but he knew it must have energy. Oh, whoopsie. Go back. All right. But he knew it must have energy. What happened there? Sorry, I'm probably making you guys dizzy. Okay. And then we had another guy, Enrico Fermi, another famous guy in physics. He called this missing particle the neutrino, and neutrino in Italian means little neutral one, because it must be little, it must be neutral, and it goes by the symbol nu. It looks like a V, but it just has like flanged out ends on the end of the V there. And he said, okay, so it looks like this. You got electron and then nu, or the neutrino that comes off of that as well. Okay, so people in physics at the time, well, it was split. Like, a lot of people didn't like this. They're like, you're just making up a particle. Like, that, you just can't do that, right? But then others said, well, we need to make up this particle to make physics not blow up. Like, we need this. So yeah. So, but the other thing that this had going for it, it didn't just save conservation of mass energy. It also saved our conservation of momentum law, because what they were seeing is that we got a proton, let's say that decays into a electron, right? It'll spontaneously eject an electron out of it. Well, what'll happen is that they can see that proton will shoot backwards. But then you would expect, right, if I've got like a proton that just spontaneously ejects an electron, that it would shoot that way and the electron would shoot that way, right? Like, how could it not? Like, that's weird that it would shoot off on an angle like that. So what he suggested is that, oh, this missing particle that we're talking about, this neutrino, it shoots off this way. And then we've seen questions like this in Unit 1. This is our like conservation of momentum. It's like a bomb, right? You've got proton goes that way, electron goes that way, neutrino goes that way, and it all adds up to 0 in the end for momentum. So it saved conservation of momentum. And then just really quickly, we're going to talk more about this in another lesson, but it also saves conservation of angular momentum. It's not the same as momentum. We think about particles, protons, and electrons as having a new sort of property called spin. And you can think about it like the proton actually spinning. But when I was in like my university courses, I was always corrected on that. It's just more of a name than anything. But it is kind of helpful just to think about it as spin. But it's like a brand new thing. It's almost like charge. You know, it's like, what is charge? Like, it's like, what is spin? It's just a new property of our proton or electron. And if that makes sense, no problem, because it doesn't really make sense to me. So, okay, yeah. So this was powerful, right? It was actually saving quite a lot to have this neutrino, but it was mysterious and like ghost-like, right? Like it was really hard to be detected because this thing is like virtually massless, or maybe massless. So it doesn't really interact with anything. So you try to set up like a detector to try to find this missing neutrino, it just passes right through the neutrino or the detector like it wasn't even there, right? So what they've actually gone to like crazy effort trying to find these things, and it was found in 1956, and it ended up having a 0 rest mass. So it has a 0 mass essentially when it's not moving, is what rest mass means. And remember why they have to make that distinction. That's because E is equal to mc squared. Right? So it actually matters whether the thing is moving or not, because if it's moving, it actually, we're not going to go into that in this course, but if it's moving, we can't use this equation anymore, because it actually has energy now, which kind of blurs the lines between, you know, mass, because mass and energy are the same thing. So it gets kind of confusing. It's called relativistic mass, or mass energy. But we won't talk about that. We can just say when it's not moving, it has a 0 rest mass. So we'll just keep things simple. Simple. It's probably not that simple. Okay. And this thing travels at the speed of light, like a photon. And it has a spin of a half, like they were expecting that it must have to keep our conservation of angular momentum. Okay, so more recently, it was determined that a neutrino isn't actually massless. It has a mass, but its mass is 27 electron volts per speed of light squared. And remember where that comes from. That's just mass is equal to energy over speed of light, right? Just rearranging E is equal to mc squared. And it's only 27. That's extremely small. It's actually 19,000 times less than an electron. And remember, when we're talking about the electron, it is like ridiculously less than a proton. So this thing is like inconceivably small. But even if, like, this is actually a huge deal in cosmology. So cosmology is talking about space and how the world, or how the universe evolves. It's a big deal there because there's so many neutrinos that just are always passing through everything in space right now. It's passing through you and me right now, like trillions of neutrinos, that if these neutrinos have any mass at all, it's really going to affect the fate of the universe. So whether the universe is going to expand forever, or whether the universe will one day start to contract, which is weird to think about, that the universe might actually start to shrink back in, and like instead of having a big bang, it'll be a big crunch. It'll all go back together again at one point. All right. So now the neutrino was discovered. We had another genius, Paul Dirac, developed a relativistic equation. So you don't need to know too much about this. It's talking about like when things are traveling close to the speed of light for the electron. So it's now known as the Dirac equation. I never got a chance in university to look at the Dirac equation or what it was all about, but apparently it describes how electrons behave or should behave in an electromagnetic field. But what kept on happening in his math is that he kept on getting a negative solution. And I just want to talk about math for a second here, right? So you guys that have taken, my math courses or just any math courses, you'll know that sometimes we get answers in math that are called an extraneous solution, right? Like it's like a solution that doesn't work, like it doesn't really mean anything in the real world. Well, that's what Dirac was thinking he was getting. So when he was getting these negative numbers, negative numbers for like a negative energy for his equations, he was kind of ignoring them like they were extraneous solutions, because that does happen in math, right? So he's like, okay, that's just a weird irregularity for the math, for his equation that he was getting, right? But more and more he was figuring out that he couldn't just ignore it, and he proposed, because of his equation, this thing called an anti-electron. And this is really getting into something called antimatter. So it turns out that there is a thing called an anti-electron. And if you think about an anti-electron, right? Remember, a normal electron was 0 for nucleons, -1 for its charge. So what do you think an anti-electron would be? Well, it's going to be still 0. It doesn't have any mass, right? Or really, really small mass. But it's going to be +1 for its charge. So you've got electron and you've got anti-electron. These things are like polar opposites of each other. And it turns out we got the same with a proton. All right, so we have the anti-electron, right? And it also just goes by the name positron. So we've got, sounds like a transformer, doesn't it? So we've got a positron instead of an anti-electron. They mean the same thing. Okay. Again, now that we've got this idea of antimatter, so there's like anti kind of everything, all the particles that we know of, turns out that there's actually there's a neutrino and there's an anti-neutrino. And so neutrino is just the symbol nu, and then anti-neutrino, and really any anti-particle, what we're going to do is put a little dash on the top of it that just means it's the anti version of it. All right, so we have to re-look at our beta decay, because there's actually going to be two types of beta decay. There's going to be something called beta minus decay and beta positive decay. Very important. This definitely comes up. This is like the whole point of everything we've done here. Where beta minus decay would be this. So it goes from some particle, so in this case a neutron, it decays into a proton, and then in order to make this all work out for our charge, right, it has to be an electron. We've talked about that. But here's the new thing. Beta minus decay is always going to give a electron and a anti-neutrino. They're like the opposites of each other. You're going to get like the real electron and the anti-neutrino. Okay? And then the next part here, down to beta positive decay, it's the flip version of it. So this will happen if you've got a proton turning into a neutron, right? It decays into a neutron, and it will emit a anti-electron or a positron and a real neutrino. So again, they're like the flipped version of each other. So now we get an anti-particle with a real particle. So just make sure you guys get those right. That's like, there's lots of ways they'll ask this. They really want you to know that you're getting the opposite type of particle, right? So you get like positron, real neutrino, electron, anti-neutrino. That whole thing is really important. And yeah, so you guys can look through that. It kind of talks about the same thing I was just doing. But just note, I've been talking about like a lot of the history of like, you know, how they found a lot of these things. Conservation laws applied to beta decay. There is some of it goes beyond physics 30, but I think it's really important just to understand the whole story and why they came up what they did. But in physics 30, you're really like it's this. This is really what they want you to understand. This whole idea of beta minus decay or beta positive decay and what happens there, right? So you're responsible for that. All right, gamma radiation. Man, I talked about making this a short one. This isn't going to be a short one. Okay. So gamma radiation, I've talked about this already. It turns out that we can talk about these energy level diagrams again for the actual nucleus of an atom itself. So if you've got a transition from, you know, one energy state down to another energy state, like it's just unstable, it's not very happy where it's at, then it's going to emit a photon. That's a terrible photon. Photon. That wasn't much better. At a really high energy, right? Much higher than like the light that we see at the visible range. Yeah, so it's going to keep, like if you emit a photon though, you're going to stay with the same charge number, so conservation of charge, and you're going to stay with the same number of nucleons, right? Because all you did was emit a photon, right? So the atom itself is the same. And why this will happen quite often is because right after you get an alpha or beta decay, right? So you get some parent nucleus decays into a daughter nucleus, that, like what we have here, right? So you've got boron decaying into carbon. Well, it'll change. It'll change the number of, or the charge on this guy, right? So then it would emit an electron and an anti-neutrino, right? Beta minus decay is what just happened there. And then see this little star? That little star there is saying that this thing's unstable. It's going to be in a higher energy state than it wants to be, right? So this carbon, right when it was created with an energy level up here, right? So then this doesn't like being up here, so pretty immediately, fractions of a second, this thing is going to jump down to the ground level and emit a photon. So emit a photon. Okay. Now, biological effects of ionizing radiation. This is gonna, I'm gonna let you guys just read this one. It is more of a reading thing. So look through here. You guys are responsible for understanding the health effects that radiation has. I'm not gonna get too much into it, but I do require that you guys read page 808 and 809 from the textbook. The good news is, on your copy of this thing, I've actually put those two textbook pages right in a few pages down here. But I'd like you guys to read both, okay? So there's just a bit of a homework assignment there on reading those. Okay. Decay rate and half-life. So good news is, if you guys have taken Math 30-1, you've seen this before. This is really like it's a logarithmic or an exponential equation, right? What's going to happen here? Like, so some of this will seem familiar. N is going to be the number of radioactive nuclei remaining, right? So when we're done, that's what N will be. N naught, or N at times 0, is going to be the original number of radioactive nuclei, or original mass, or original activity of the material. Notice that there'll just be different wording for these things, but we'll use the same equation. And then the 1/2 here, just while we're thinking about this, if I'm multiplying something by 1/2, right? Let's say that this is just 1 for a second for my exponent. That's going to be smaller, right? Well, this makes sense because what we're going to be seeing here in a second is a graph that goes down like this. So this thing I'm expecting to get smaller and smaller over time, as opposed to if this thing, let's say, was the number 2, then that would be a graph that looked like that. So it's going to look different, right? It's the decay part of this. And then the next thing to make sure you guys know here is this one. So on your formula sheet, it's written as n, right? So it's just to the power of n. Well, n actually means this, where t is the time that's gone by, and t 1/2 is the symbol for the time for one half-life. So really what's happening here is you're saying it's the number of half-lives that you have. So let's say if you've got 20 years goes by, so that'd be your t. So here, n is equal to 20 years goes by, and it takes 10 years, or let's say 5 years, 5 years for half-life, for each half-life. Half-life. Okay, well then, you know, how many half-lives have gone by? Well, that's just 20 divided by 5, right? So there's been 4 half-lives. So that's all this is saying. So n is the number of half-lives that have actually gone by. Okay, so like a picture of what we're talking about here, right, is that if you had all parent nuclei to begin with, so you've got 100%, well then after one half-life goes by, well now you've only got 50% left, right? And then after 2 half-lives goes by, well now you've only got 25, because that's half of 50. And then after 3, well now we've only got 12.5, right? So that's what's that's all that's happening here, right? Okay, so type of question that you get, it says the half-life of a radioactive isotope is 2.5 years. So just while we're thinking about this, n is equal to time over time 1/2. The half-life of a radioactive isotope is 2.5 years. That's talking about the bottom number here. Okay, if the activity of the original sample of the isotope was this many Barkels, what is the activity after 5 years? Well, 5 years, that's the top number, right? Okay, so you can see n is there, plug it all in, and you get your answer for the number that's left, right? So this could have been written in like number of actual atoms, or you know, there's, like I was saying, there's different ways to write it up here. So mass or activity of the material, and that's what it was written in here, was the activity of the material. Alrighty. So again, you guys can look through those. They're going to be kind of similar. So if you're given a curve like this one, right, and you wanted to figure out what the actual half-life was, like what the T1/2 is in our equation, n is equal to time over t, what the half-life is. Well, we can figure this out from the curve by, like, you'd figure out 2 points, right? So if I start, let's say, at this point, so n naught, then well, all I'm going to do is you'd go halfway down the graph, right? So if this is the bottom, you'd find the place right in the middle, just based on what your numbers are down the side. And then wherever that lines up with your graph, that would be 1 half-life. And you're pretty good to go from there, right? Because now, you know, 1, 2 of those, I'm going to end up with the next one, and then another one, you know, and that's how this half-life system goes, right? So the next one would be half of this, so it would be, you know, down there, right? All right, practice problems.